This video is about multiple regression, and as you can see, regression is part of the inferential statistics, and the multiple regression is a further development of the simple regression. The difference here is that instead of only having one independent variable, we have more than one independent variable. So instead of only using one variable to predict our outcome, now we use multiple variables to predict outcomes. You can see this as well. Instead of just having one b, we have a b1, b2, and so forth. Instead of having a small r square, we have a big r square. And we have then also different tests between the different models. So the main difference between simple regression and multiple regression is that there are two or more independent variables, so two or more predictors, and the sample size, usually a rule of thumb is that you have at least 10 times as many cases as independent variables, preferably more than 50. So why should you care? What can you do with multiple regression? Well, the interesting part is that now we can compare different variables with each other and decide if one of these variables is a more adequate predictor than the other. And we can actually formulate stronger models. So instead of predicting outcomes just with one variable, we can use multiple variables to predict our outcomes. So we can make better and stronger models. So the r squared now, if you remember right, was basically the squared correlation between two variables, right? If we predicted y with x, the common variance was our r squared, the variance that they had in common. Now we have not just two variables, but we have one criterion variable, so one outcome variable, and we might have two predictor variables. So potentially we can not only explain the yellow and blue part here, but we can also explain this other part. So we can explain more of the variation of the dependent variable because we have more predictors. Right? And if you have more, you can increase that. Right? We can explain more and more of this variation. However, an issue could be the problem that's called multicollinearity. That's the correlation between the predictors. Right? Ideally, we'd have no collinearity. Collinearity means the correlation between two or more predictors. So this is great, right? Low collinearity is also okay, right? We increase the variance here that we explain of this variable y. But as we get high or very high collinearity, you notice the overlap between x and y. And this overlap can become a problem because our coefficients of our predictors might become unstable, or they might be difficult to interpret. Sometimes you even have the signs that start switching on you, or something that's normally positively related to an outcome all of a sudden has a negative coefficient, which wouldn't really make a whole lot of sense. The diagnostics of multicollinearity, we have two indicators, width and tolerance, that can help us decide if we actually do have a multicollinearity problem. The width rule of thumb should be smaller than 5, and the tolerance should be larger than 0.20. If it's smaller than 0.20, then we have indication that we have a problem of multicollinearity. If that is the case, what do? We drop a variable from the regression. So if you have two variables that are highly correlated, we eliminate one. Or one other way to do it is to combine the variables. Those are two approaches to deal with multicollinearity. Also here, a number of assumptions that are assumed by the multiple regression. And here a side-by-side comparison of simple versus multiple regression. Both of these have one dependent variable, but we have in the simple regression just one regression coefficient, whereas for the multiple regression we have a coefficient for each independent variable, so for each predictor. And then the small r squared is a proportional variance explained by the predictor variable, and the large r squared here is the proportional variance explained by a combination of predictors. Here is the regression formula for the multiple linear regression. And you notice the start is the same, right? Y is our outcome equals the beta 0 plus beta 1 x1. That is the simple regression, right? Plus the error. That would have been the simple regression, just one predictor here, beta 1. And now the only difference is for multiple regression we start adding other predictors, so beta 2 x2, then it could go beta 3 x3, beta 4 x4, etc. And then here as a placeholder you have beta p xp to indicate that this could go on and on and on. Alright, so here you can see the formula. Then to calculate the multiple regression, multiple correlation coefficient, we now don't just have one variable, but we have multiple variables. Here are the formula. And then we can calculate the standardized coefficient, the partial standardized coefficient, which extracts some of the variance of other predictors. And here is an example of how you could calculate the r squared. And here is an example of how you could calculate the standardized partial beta coefficients. And here an example that we can walk you through in SPSS.